Good afternoon and welcome to the Safer Sim webinar series. I am Dawn Marshall, Director of Safer Sim and a Research Manager at the University of Iowa. Safer Sim is a Tier 1 University Transportation Center with the research priority of promoting safety. Our webinar series features research projects from the Safer Sims Consortium, and thank you for joining us today. There will be time at the end of the presentation for questions and discussion. You can use your microphone or the chat box to participate. Feel free to use the chat box at any time throughout the presentation as well, and we'll address any questions or comments shared there during the discussion session. This webinar is being recorded and will be shared online within a few days. Today's presentation features a project from the University of Central Florida, and I'm pleased to welcome our presenter, Dr. Yu. Dr. Yu, please take over.
Thank you, Dawn. Thank you, Dawn, for holding this wonderful webinar. And I'm Lishengsa Yu, and today I would like to introduce our research about investigation of merge strategies at the ramp area in connected vehicle environment by using our self-developed multi-driver simulator system. In our research, we select the freeway merging area as our study area because this area is very special, that it contains a lot of complicated vehicle interactions. It's typically a crash conflict hotspot due to the vehicle interactions. So if a driver failed to observe his surroundings or failed to have a correct perception of the situation, the driver may be very likely to have a conflict or even crash with others. And also this situation is also being interested by some autonomous car companies. For this specific situation, they would like to develop some autonomous driving algorithms. We say that in addition to traditional targets in terms of the driving safety and driving comfort, we also have some other expectations for an algorithm, for a CAV Merge algorithm to be a good algorithm. That is, we would like the algorithm to disturb the mainline traffic as little as possible. In other words, we not only want to have our target car, which is embedded with these algorithms, driving safely and driving comfort, but also at the same time, we want it to interfere with others as little as possible, so that others, particularly other human drivers on the main lane, can continue their normal drivings without affected by these merging CAVs. Traditionally, we have several ways to evaluate whether a CAV merge strategy to be good or not. The first method is the macroscopic simulation based on some Vision, Sumo, Amazon, or other simulation platforms. The issues related with these simulation tools is that there's no realistic driver behaviors. We also can conduct some field testing. In a field testing, we can have some realistic driver behavior, but the thing is, due to some safety constraints, we cannot test the vehicles to be a very high speed. If we look at the previous studies, we can see that the most studies were conducted on a speed limit of 30 miles per hour. The speed above 30 miles per hour can be regarded as very dangerous in a field testing. The third method is the simulator. Specifically, is a single driver simulator. So in a simulator, we can test the alien situations or like even some very dangerous situations in the reality. The thing is, there's no vehicle interaction for a single vehicle simulator. To solve these issues, our UCF developed our own simulator system, which is a multi-driver simulator sets, so that many drivers can be joined in this system and can be communicating with each other at the same time. So in this system, we have the realistic driver interactions, and we have no safety concerns, so that we can test the many situations. The objective of this project is to evaluate the influence of the different merge strategies on human-driven vehicles at the mainline. We use our multi-driver simulator system. And in this project, we mainly look at two classical types of the merge strategies. The first type is the reference trajectory-based merge strategy. And the second type of the algorithm is the social psychology-based merge strategy. So these are some pictures, photos of our developed simulator system. In the picture, we can see that three simulators are connected with each other. And on the bottom one, we can see there's a detailed view of what the drivers can see in the scenario. And we see some yellow words showing on the middle screen. That is the driving instructions provided by our algorithms. So the figure on the left hand is the structure figure about our system. We have a data collection module. This module can collect the not only the steering wheel, the pedal, the brake, all these equipments, status and positions, but also it can collect all three drivers data in the simulator. And we also have a scenario management module, because in the scenario, we need many triggers to activate some specific vehicle movement. So through this module, we can connect each dynamic object in the scenario. We also have a vehicle physics module, which is we write a code about the vehicle engine, about the engine sound or other physical effects. And the most important module is the communication module, which enables us to communicate the three drivers together to share their locations, the positions in a simultaneous way. In terms of the merge strategy, the first type of the strategy is the reference trajectory-based strategy. And the core idea for this algorithm is that the algorithm will keep generating a reference trajectory to get our CAVs. So the CAVs is supposed to arrive at a specific point. In our experiment, this is the merging point at a specific time and at some specific speed and acceleration. And we can see that from the equations for these algorithms, it's mainly trajectory-based equations. The second types of the strategy is the social psychology-based merge strategy. So we can see from these equations that the critical parameters are the speed, specifically is the desired speed or desired expected speed of the drivers, the safe speed, which can be acceptable to a driver, and also some other desired distance. All these critical parameters are related to the driver preference. So that is why we call this strategy is the psychology-based strategy. Basically, all these equations are trying to convey what is the preference of our human drivers. So in our experimental scenario, we analyzed two scenarios. The first scenario is the merging period. So it starts from the time point that our algorithm starts to work to the time point that the CAV arrives at the merge point. The second scenario we investigated is the following period. So our CAV will, after it arrives at the merge point, it will follow the whole platoon for some period of time, and then he will left the main lane. So we will look at how these yellow vehicles, the vehicles in the platoon, will behave to the merge of the CAV, and also what drivers of these yellow cars will behave during the following period. We will look at the behaviors of the vehicles number 3 and number 2, because these two cars were the major cars that is affected by our emerging behaviors of the CAV. So one thing I would like to mention is that we need to identify what is a very important period, which is the influence period. Basically, what we found in the experiment that even though the driver can observe our CAV is merging, but in most cases they will not respond to the merging immediately, and sometimes for some drivers, they will kind of hesitate because they have no idea what the CAV at what time point the CAV will merge into the main lane. So he wants to wait a bit more to see what will happen in the next few seconds. So for some other drivers, they will respond to the merging behavior immediately. So due to this difference, we need to identify a very important period, which is called the influence period. So that is only when the CAV is close enough, the second driver will be affected and accommodate his driving behaviors to the merging vehicle. And we use a finite Gaussian mixture model to distinguish the influence period. So this Gaussian mixture model considers several variables, including the speed, the throttle, and the brake positions, as well as the distance between the cars as the indicators, so that we can distinguish a particular period which our human drivers were actually affected by our CAVs. In our study, we look at both the safety metrics as well as the comfort metrics. For the safety metrics, we look at the CTC, TET, and the TIT, these three metrics. So TTC is a very well-known metric, safety metric. While for the TET and the TIT, these two metrics basically can have a better evaluation of the whole period in terms of the TTC. So in other words, the TET and the TIT will look at the length of the period in which our TTC is below our threshold. So they will look at the TTC, how long will the TTC below a particular threshold. For the comfort metrics, we have some traditional comfort metrics, which is the jerk, the acceleration, and the minimum headway distance. So there are a bunch of the studies can demonstrate for the jerk and acceleration, there is a negative relationship between the metrics and the comfort level. And for the minimum headway distance, the relationship was positive. And in addition to this traditional three variables, we also look at the two new variables, which is the TTMT and the longitudinal quickness. For the TTMT, it is the time to minimal distance at the moment when the acceleration pedal was released. So intuitively, we can see the larger this variable, the better the comfort levels. For the longitudinal quickness, it is the ratio of the average longitudinal acceleration and the change in longitudinal speed. So what this variable tells us is that even if our average longitudinal acceleration is small, however, if this small if this average acceleration is big, it's very large. However, if this acceleration can last for a sufficient time, in other words, the change in longitudinal speed is sufficiently large, then the longitudinal quickness, the value can be very small. In that case, the comfort level should also be regarded as a very good level. So if we only look at the average longitudinal acceleration, based on our some studies, we may say that okay, this variable, the smaller the better, the larger the worse. However, this longitudinal quickness variable tells us if this large acceleration can last for a very long time, the comfort is still very good. So this is the result. We look at the second and the third vehicles in the platoon. regarding both the safety metrics and the comfort metrics. And what we can see from this figure is that so the major difference was between the AHS algorithm and the GFM algorithm. So for the third car, we can see that the AHS algorithm was always the best algorithm in terms of both the safety and the comfort metrics. Well, there's something to say for the second car. Let's take a detailed look at it for the second car. So for the second car, in the merging period, the GFM, if we look at the TET value, is regarded as the best strategy because it has the smallest TET value. What does this mean? This means that it has had a higher safety most of the time. However, the GFM has also had a minimum TTC, which means it can have a very severe conflicting situation at some time points. So, however, while the AHS had an opposite effect. So the AHS, if we look at the TET, I mean, in most of the time, it has a less better safety level. However, if we look at the minimum TTC level, the AHS has the largest minimum TTC level, which means the most critical situation for AHS is better than the GFM. So moreover, this phenomenon turned over between two strategies in the following period. We also look at the driving comfort in the following period. There's the phenomenon we observed for GFM and the AHS is also kind of debated with each other. So by looking at the TTMT and the longitudinal quickness, these two variables, we can see that the GFM gave the second car a comfortable start because it had the largest TTMT, and it made the second car constantly accelerate for a longer time because it had the smallest longitudinal quickness during the acceleration. However, if we look at the other metrics, such as the acceleration, deceleration, the jerk, the minimum headway distance, the AHS was better when compared with other strategies. Obviously, the evaluation of the AHS didn't consider the time dimension of the metric. In other words, we didn't. This metric doesn't consider how long this level of the metric lasted in the experiment. Some conclusions. So these algorithms might not have consistent performance when evaluated by different strategy and comfort metrics. In addition, merge strategies may have a variation of the effects when we look at the merge or the following periods. Basically, the AHS and the GFM may be superior to other algorithms when evaluated at some specific dimensions. Nevertheless, the AHS may outperform other strategies, even outperform the GFM, because we can see from that table it can be the AHS is better in more scenarios. Our project suggests that the CAV merge strategy should not only ensure the ramp vehicles merging task, but also consider mainline vehicles driving performance. That's it. That's it for our project. Thank you.